Bernoulli's equation is applicable to fluids. Here we'll consider a flowing liquid, and the liquid is incompressible, and we'll discuss Bernoulli's equation in reference to this flowing liquid. So consider this liquid whose density is rho. Density of this liquid is rho, and it is flowing through a pipe. This is also called flow tube. For the sake of simplicity, assume that this is a pipe through which the liquid is flowing. The pipe, as the drawing shows, has variable cross section. Here the cross sectional area is A1, and here the cross sectional area is A2. While the liquid passes through this cross section, its velocity is, suppose, V1, and when the liquid passes through this cross section, its velocity becomes V2. So this is the velocity V2 and this is the velocity V1. Area of cross section, here it is A1, and the area of cross section, here it is A2. We will have to measure the height of this cross section and the height of the other cross section from a reference. Let us consider this as the reference, which will be horizontal reference, which will be used to measure the heights of the cross section. The height of this cross section is H1, and the height of this cross section is H2. H1 and H2. By Bernoulli's equation, P1 plus rho g H1 plus half rho V1 square equal to P2 plus rho g H2 plus half rho V2 square. Or in other words, P plus rho GH plus half rho V square. The value of this expression does not depend on the cross section through which the liquid is flowing. Value of this expression as per Bernoulli's equation is constant. Now let us prove this. We'll prove this by using work energy theorem. For that, we'll have to consider a discrete mass. Because this is a liquid and there is a continuous flow, so consider a discrete mass. I am considering a mass of liquid over here, which is del m, and we'll consider same del m mass at some other location. That means around this cross section we are considering del m mass of liquid. So its mass is del m. Mass of this is also del m. And this del m mass has been pushed into this liquid column in del T second. Okay, so this fact requires some explanation. Consider this, consider liquid in this portion, consider the liquid in this portion. The volume of this liquid is fixed. Volume of this liquid or volume of this portion of the pipe is fixed. Consider a finite mass del m of liquid which has been pushed into this volume at the cross section, at this cross section. And since volume of this is constant, through the other cross section, in the same time, del m mass of liquid will be expelled. So let us consider that we have taken del T second, or this mass del m mass has taken del T second to go in. So I think you have understood this part, because the volume of this portion is constant. So if 1 liter goes in, 1 liter has to come out in order to make room for the incoming liquid. So del m, I'll now write del m. Del m equal to what? Del V into rho. What is del V? The volume of the finite mass. And del V equal to what? Del V, volume, equal to length into area of cross section. Now in del T second, the length will be V1 into del T, because here the velocity is V1. So V1 into del T is the length of this. This is V1 into del T multiplied by area of cross section. So length into area of cross section, that is del V into rho. Hence, for these two cross sections, we'll write del m equal to, one is A1 V1 rho del T, and the other one is A2 for this mass, A2 V2 rho del T. Okay. Now, so this is one. Now, let us apply work energy theorem. Work energy theorem is W net equal to del K. Now, what exactly is W net? W net is the work done by, I am telling by, it is not against, work done by all the forces. Okay. Now, these forces include conservative force, non-conservative force, all the forces. So work done by all the forces, work done by all the external forces. This is another important point. All the external forces on del m is equal to change in its kinetic energy. What is the change in its kinetic energy? Half del m V2 square minus half del m V1 square. Now, in order to find work done by all the external forces, we'll have to identify the external forces first. What are these external forces? The external forces are, first of all, thrust exerted by liquid which lies behind this del m, behind this, because our system comprises of, this is our system, see, the liquid in this portion is our system. So liquid lying here is external to the system, and liquid lying here is also external to the system. Here the pressure of liquid is P1. Here the pressure of liquid is P1. So that will exert a force P1 into A1. Here the pressure of liquid is P2. And therefore that will exert a force. Or thrust, which is P2 into A2. So this is P2 into A2. This is P2 into A2. Okay, so these two are the external forces. And then there is weight. Weight is due to the external force of gravity. Weight is due to the external force of gravity. So this is another external force, which is del mg. Del mg. Del mg. And there is another external force, which is the net force exerted by the wall of the pipe. Net force exerted by the wall of the pipe. The wall of the pipe exerts a net force, which is N, the normal force, which is N. Hence, now W net. Now W net equal to W work done by mg plus work done by P1 into A1 plus work done by normal force plus work done by P2 into A2. Please note that all these are external forces. Why all these are external forces? Because our system comprises of this portion, the liquid in this portion, and therefore the liquid outside on the right hand side or on the left hand side exerts forces which are external. This is equal to work done by. Okay, so should not confuse yourself. It is the work done by mg. Now mg is downward, but this has gone upward. The displacement, vertical displacement, is h2 minus h1, which is upward. Hence the work done by mg is negative. This is equal to minus del mg into h2 minus h1, minus because the force and displacement are oppositely directed, plus P1A1 is the force multiplied by the displacement in del t second. The velocity is v1, so the displacement is v1 into del t in del t second. So force into displacement. This particular work is positive because force and displacement are in same direction. Work done by normal force, the net force exerted by the wall of the pipe, that work is 0 because it acts perpendicular to the displacement. Displacement is along the length of the pipe and the force and normal force is perpendicular to the length of the pipe. So this work is 0. Then work done by P2A2. You can see that P2A2 is towards left while the mass del m displaces towards right. So for P2A2, force and displacement are oppositely directed, and that's why the work done by P2A2 will be negative. P2A2 is the force. Now we'll use equation 1 and we'll replace A1 V1 del T. Okay, we find A1 V1 del T here. A2 V2 del T here. So in place of this A1 V1 del T, we'll write del M by rho. So let us write this part, del mg H1 minus H2 plus P1 into A1 V1 del T, that will be written as del M by rho. Okay, and then P2 A2 del T, this part A2 V2 del T, that will be written as del M by rho. So this is del M by rho equal to change in kinetic energy. And what is change in kinetic energy? Change in kinetic energy is, now I am writing del K equal to half del M V2 square minus half del M V1 square. By change, all of you know that change is final minus initial. So final kinetic energy is half del M V2 square and initial kinetic energy is half del M V1 square. Now I will apply work energy theorem. Hence del mg H1 minus H2 plus P1 del M by rho minus P2 del M by rho equal to half del M V2 square minus half del M V1 square. Now cancel del M. Hence we get this G H1 minus G H2 rho plus P1 minus P2 equal to half rho V2 square minus half rho V1 square, or P1 plus rho G H1 plus half rho V1 square P2 plus rho G H2 plus half rho V2 square. Hence proved.